I'm glad you're having fun with it. All right. So some of these we did some very much like them yesterday. So let's see what's happening here.
Number 4.
Because it's one of those ones that people get their brains stuck on, so it pops up every now and then because we're trying to preventatively unstick it. So we're trying to figure out what these equal, what these are equivalent to. And the best way for us to kind of think that is to think about our B, P, A that we change into our log base B of A. Hey, thank you. That equals B. So we're trying to figure out the piece that's missing over here. And on all 4 of these, it's missing that power, that variable P. So we're not trying to figure out what this guy is. So on these ones, the kind of easiest way we've got to do it is to switch it back to our exponential form and use a little bit of logic. Because what we have here on our first one is we have that our base is what? 5. We know our argument is the 125, and we're trying to figure out what power goes here to make this true, which I definitely put this all in like the wrong row. There we go. We're going to move it down. So what power would go there to make this true? 5 to the what is 125? Cubed, 5 to the 3rd. So what that tells me is log base 5 of 125 equals 3. So it's a way of saying the base to what power equals this number. So for number 2, the base to what power equals our argument. So 7 to what power equals 7. So 7 to what power does equal 7? So our power would be 1. 7 to the 1st equals 7. So log base 7 of 7 equals 1. Anytime our base and our argument are the same, the power will be 1. What about for number 3? Yeah, because this is 12 to what power equals 1. Well, the only thing that's going to knock things down like that to 1 is if our power is 0. 12 to the 0 equals 1. Because anything raised to a 0 power equals 1. And for number 4, we get 4 to what power equals 1/16. -2. Because the negative is what gives us that fraction, and 4 squared gives us 16. So log base 4 of 1/16 equals -2. Because our 4 to the power of -2 equals our 1/16. So we don't necessarily have to write this step. It's a fine way to especially double check. We don't necessarily have to write that step down. Okay, questions on our evaluating stuff? Okay, so we are going to be in our packet. Shock. That is going to be a phrase we use pretty much every day. And we are going to be on page 3, which the page number does actually show the whole number there. It's not cut off in a weird way like the 2 was. And we're going to do everybody's most favorite thing. Graphing. So we are going to have a surprising number of tables on these graphs. which means, especially when it comes time for things like tests, please write in the dang on tables. Stop doing this stuff in your head. There's space. Use it. Write it. If you ever need more space, I'm happy to give you more paper. I have piles. Piles upon piles of paper. I'm happy to share. At any time, for any reason. Write stuff down. All right. So, what we're going to start with, our very first one, number 1, is that we're going to graph log base 3 of x. And what we're going to remember when we're doing this is that we made logs. The whole reason we have logs is to take an exponential, like, say, 3 to the x, and take my x and my y and have them change places. Doing the inverse, because these are inverse operations, just like multiplying and dividing, just like squares and square roots. Exponentials and logarithms are inverse operations. So the way we're going to graph logarithms is we're going to start with an exponential to make our logarithm. So just like when we did exponentials last chapter, our parent function comes from the base. So I'm going to look at this base right here. We have log base 3 of x. And what that means is we're going to start by looking at the table of 3 to the x. We take our base of 3 and we're going to make our exponential. So that's going to be the first table I make. When we're making an exponential, what x's do we pick? Perfection. -2, -1, 0, 1, and 2. And exponential functions have an asymptote at y equal 0. What y values do we get for 3 to the x? 1/9, 1/3, 1, 1, 3, and 9. I'm going to go ahead and plot this up. This is going to be the only time we're going to graph the exponential is on this one. So let's graph our exponential so we can see what's happening here. So our -2, 1/9, our -1, 1/3, 0, 1, 1, 3, and 2, 9. And again, it's got that exponent or the asymptote, that line we cannot cross right on our x-axis here. So I'm just going to connect these up. Ooh, that's too thick. There we go. Let's go with that one. Better. So it's going to go like this, and it goes off to the side forever here. So this is our exponential function that is 3 to the x. But we aren't actually asked for 3 to the x. We are asked to find log base 3. But what we know about exponential functions and logarithms is they are inverses of each other. So just like we did when we first made inverses and we took a list of points where I took my x's and my y's and we made them change places. We're going to do that with our table. I'm going to take my x's and put them in the y column. And I'm going to take my y's and put them in the x column. And that's going to give us our inverse. So to find our table for our log base 3, I'm going to get a dark blue now. For our log base 3 of x, we take the inverse of the guy we just made. So what was the x's becomes my y. So my y's are going to be our -2, -1, 0, 1, and 2. What was the x becomes the y. And then also what was the y becomes the x. So we have our 1/9 in the x's. My 1/3 in the x's. 1, 3, and 9. And what was a y on our asymptote here becomes an x. So our asymptote is going to be at x equals 0. So just like on our exponential function, how our x-axis was our asymptote here, now it's going to be our y-axis that's our asymptote for the log. So when we plot this up, we're going to be real careful because I have 3 points in this little gap right here. When my x is 1/9, that's just right here, like just barely past my y-axis. So when x is 1/9, we have a y value of -2. So we have a point right here. When my x is 1/3, so just a little bit farther, we're down at -1, so we're right here. When x is 1, we have our point at 0. When x is 3, our y is at 1. And when x is 9, our y is at 2.
Wait, this looks familiar.
So this,
Wasn't this on our SAT practice questions?
oh, we've seen these, yeah. I believe it was, just to kind of look at things. Should look like that. These are inverses of each other. And we could see that if I folded this diagonally, like if I could digitally take this and I could fold it crosswise, diagonal, they would line up exactly, which is what happens with inverses. So our asymptote on our logarithms is going to be a vertical asymptote. So it's going to be up and down. So for our parent functions, our asymptotes are always going to happen at that x equals 0. What is our domain for our logarithm here, for our blue piece? The dark blue piece, excuse me, because they're both blue. What's our domain going to be?
Negative positive?
Does this go to -infinity?
Wait, no.
Because this is an asymptote right here for our logarithm. So it's not going to cross this wall. We have an asymptote right here, a vertical asymptote. So it's never going to cross that. So it's never going to go below 0. So our domain is going to be from 0 to infinity.
Oh, yeah, because it's the inverse.
It is the
Okay, yeah.
inverse of our exponential. So what was the range of our exponential function becomes the domain of our log. So what was the domain of our exponential function becomes the range of our log. So what is the range of a log?
Of a log.
Of a log. What is our range going to be? Think about what was the domain. This is the one that's going to be -infinity to positive infinity. -infinity to positive infinity. Because this is still going up. It will continue to go up. Out of the corner of the building, out into space, out into South Kentucky. That way.
Hold on. How does Kentucky
South.
go after space?
Well, I was going up that way. We're going over a lot farther. We would probably hit Kentucky before we got to space. Just don't say we go beyond infinity because Buzz Lightyear's wrong. Okay, so this is how we're going to find our parent functions for logarithms. So just like for every exponential function, we had to write kind of a new parent function. This is going to be how we get to our parent functions on logarithms. So when we start doing our transformations here, and the next one, we're going to wind up with 3 tables. Our exponential table that we use to make our log, that's our parent, and then we're going to apply our transformations. So we can get 3 tables on these. So if you need colors for things, I have colored pencils, I have markers, I have highlighters. I am happy to provide you with that. Y'all know how I color code stuff. What's up? You want some colors? Yeah, Archie has. Okay, before I do that, I'm going to put up here our transformation form. I know we wrote it on the very first page, but we had no idea what we were writing. So I'm going to put it up here. There's a line for it in there, our transformation form for our logarithms. So write this on that line. Now we've seen a couple of things with our logs. Now we kind of know somewhat a little bit of what's happening here. It will feel less squeaky. Very familiar things in here. We've got our A that's going to do our stretch or our compress, our reflection across the x-axis. We've got our H that does our horizontal shift. It still has a minus sign, so it is still going to be that opposite of what we see in our expression. And then we have our K tucked on the end, and that does our vertical shifts. So A, H, and K still have those same jobs they have had since we started using them in August. The only piece in here that's different than anything we did in August is that we have the B as our base, and we have to do our transformations that way. What's that?
And also log.
And also the word log. But to be fair, we don't actually log anything in this one. So we're going to do our first one. Lots of stuff on here. So we are asked to graph log base 2 of x and log base 2 of x plus 4 minus 3. So we're going to do our first set of transformations here.
Why does yours is transformations and then ours doesn't?
Because I type things up in a different order. So we will identify our transformations. We're going to have to find A, H, and K for us to be able to make our transformations anyway. We'll just talk through it. Probably that's there so I don't forget to ask us to talk through it. Because I get excited. I'm like, I want to draw the pretty pictures. So sometimes I get excited and forget to do the important math things. All right, so what we're going to do is we are going to start by trying to graph our log base 2 of x. This is the guy we want to get to first. This is our parent function. I do not like how dark that purple is, but that's okay. We'll rock it. So before I can do anything with our log base 2 of x, we need to come in here and say, hey, it's a base of 2. So what we're going to start with is actually our 2 to the x exponential. We are not going to be building the table purely from logs. We are going to use the fact that they are inverses of each other. Those of us that are on our cell phones right now are shockingly confident in our ability to do this without ever practicing it. We're picking our x's to find our y's. So with our exponentials, that's when we usually use our -2, -1, 0, 1, and 2. And they have their asymptote at the y equals 0. What y values do we get for the 2 to the x exponential function? Mm-hmm. 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 1/4, 1/2, 1, 2, and 4. Rock on, Marley. So we use that to get our logarithmic parent function. It's a mouthful right there. Because we take the fact that log base 2 of x is the inverse of that exponential. We are not going to graph all 3 things. We are just going to graph our 2 logs. So I'm not going to graph my light purple there. I'm going to use that to build my log parent function. So what was the x's is going to become the y's. So everything in the x column goes into the y column. So my -2, my -1, 0, 1, and 2. What was in the y column is going to go in the x column. My 1/4, 1/2, 1, 2, and 4. And then again, what was a y becomes an x. So our asymptote for our parent function happens at our x equals 0. Yes, dear.
He says it's okay if we use different colors.
Say it again for me.
He says it's okay if we use
Oh, absolutely. 100%. And if you ever need more colors, I have a whole bucket. And I also have markers if you don't have colored pencils. And highlighters and a variety of things. And if you like something else, I probably have it. I just didn't get everything out craft-wise. I have a vast variety of coloring options. If there's anything ever I can get you, please let me know. My craft supply closets are very full.
Probably won't want to use your pens.
My expensive pens, no, but I have other pens.
The pens, do you have purple?
Not in the ones that I give out. Because, no, I keep all the purple ones. No, you can go buy your own $2 pen because those purple pens are for $2 a pop.
Dang.
That's why I don't share.
Do they not come in like the packs?
Oh, they come in the packs, but if you buy them, like you can go to like Michael's or Joann's or something and buy pens individually. They're $2 a pop if you do that. All right, so our logarithmic parent function, I am going to draw that one up here. When our x is 1/4, our y is -2. That's about here. When our x is 1/2, we're at -1. When our x is 1, we have a 0. When x is 2, we're at 1. And when x is 4, we're at 2. So we can see our parent function looks like this. I should have picked a lighter purple, but that's okay. But that's our parent function. I'll just do like a very, very dark purple for the transformed. So that gives us our parent function. Then we're going to make our transformation, which we are going to do 100% the exact same way we did for exponentials, where we take our x plus h, and we always remember how much graphing makes us yak, ya plus k. But that requires us to know what a, h, and k are. Yes, dear?
We don't have to graph 2x.
We are not going to graph the exponential function on anything except for that very first one so we could see what it was. We just use this as a tool to build this. So we will wind up with 3 tables, but only 2 graphs on the line, or 2 graphs on the graph. So we need to know our a, h, and k for this guy. So what is our a value for our transform function over here? 1. It's the number multiplied out in front. What that means is we do not have any a transformations. There's no stretch, there's no compress. It is what it is. I'm going to scoot this up just a bit. So our a is 1. What about our h? What's our h going to be? Careful, careful, careful. -4, which means what direction do we expect this to move?
Yeah.
H of -4?
Oh, left 4.
Left 4. H does the hula, goes side to side. Give me just 1 second. All right, and then what's our k for this one? Because our k is tacked on the end over here. So our k is going to be that -3, which means what do we expect to happen transformation-wise? Down 3. So that's this guy here. So when we're doing our transformations, what we're going to do is exactly like we did in the exponentials. We're going to take our x's from that parent function, and we are going to subtract, or we're going to add h. But in this case, our h is -4. So if we add -4, it's the same thing as -4. And we're going to take our y's from our parent function. We're going to go times a, which in this case is 1, so that's not going to change anything, plus k, plus -3, or -3. And for some of these, we're probably going to want to use a calculator for them. And that's okay. So we're going to take our x values from over here, and we are going to apply this transformation. So we're going to take our 1/4 and take away 4. Yep. Yep, you will.
Did you get this from Speech and Games? Because she has like.
No, it just randomly showed up in my room. So it just wound up in the box. I'm just saying, there's a couple of items that have just been left in here that have wound up in the fidget box because I'm not going to take them home. All right, so yeah, we are going to wind up with some fractiony decimally gross x's, and that's okay because we get on our very first one with our 1/4 minus 4, we get a negative 3.75 or negative 3 3/4. For our 1/2 minus 4, we get negative 3.5. For our 1 minus 4, we get negative 3. 2 minus 4 gives us a negative 2. And 4 minus 4 gives us a 0. I'm also going to grab my asymptote right here. Since it's an x, we're going to do the exact same thing. I'm going to take my 0 and -4 to get my asymptote's going to be at x equals -4. We apply our transformations to our asymptotes as well. Since it's an x, it goes through my x transformation. Just like with my y's, went through my y transformation on my exponentials. Our y's, we're going to do the very same vibe. I'm going to take my -2 times the 1, which is still -2, and then -3. Which is going to give me a -5. I'm going to take my -1 times 1 and then -3, which gives us a -4. The 0 times 1 minus 3 gives us a -3. Then we have a -2. Then we have a -1. So again, before I start plotting up any of these points, I am going to put my asymptote. I don't typically draw my asymptote for my parent function because it's going to be our axis, but with our transformed functions, we need to draw in our asymptote. So this is going to be where x is -4 and x is stuck at -4, which means we've got ourselves a vertical line through -4 over here. So where x is -4 is our asymptote. So this is our wall that our graph can't crash through. Logarithms are not the Kool-Aid man. They cannot go through. They are stuck. So graph our asymptote. And our asymptote happens at our x equals -4. And then I can plot my points. But I don't want us to plot our points before we get our asymptote on, or we will get things kind of askew and off. So we need to be really careful because our x's get real decimally over here. So we have our -3.75, -5. So that gives us a point down here. We've got our -3.5, -4. So we're here-ish. Very, very similar. -3, -3 gives us a point right there. -2, -2 gives us a point right there. And 0, -1 gives us a point right there. So this is gonna look like that. Oh, the very dark one? Oh, yes. I was gonna say, I have a limited color selection, but the variety of purples is not awful. Okay. Questions on that part? Last bit on this question. What is our domain of the dark one, the dark purple one? What's our domain? What's the smallest it goes? What's the biggest it goes? The -4. Good. It's always going to involve our asymptote. It's getting as close as it possibly can to that asymptote without going through it. It's going to get very, 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 very close. It's always going to be your asymptote. It's either going to be on the left or on the right, but your asymptote's always going to be there. So our domain is going to go from -4 to infinity. Are we ever going to switch it the other way? I was like, I don't know that we're ever going to have it go the other direction. Yeah. That's kind of a, I think a pre-cal would do that, but not in here. I had not. I was about to. What is our range going to be? -infinity to +infinity. For logarithms, that's always going to be our range. Every single time. 100%. If we had access to every single time I was going to ask you for the range, you could go fill them all in right now. Every single time, our range is going to be -infinity to +infinity. Okay. Questions on this one? That gave us kind of a little example of absolutely every piece of this. We're going to practice more with these tomorrow because they do take a little bit of time, especially when we're just getting used to them. So we're going to work with these more tomorrow. Technically, you guys could do the homework now. For 8-1, you could finish it out. You don't have to because we're going to do more graphs tomorrow because we've only done one and we haven't even used an A yet. But we've used A's before. It doesn't change how we do it. We just gonna practice them tomorrow. Okay? So, but with 6 minutes left until announcements, I am not gonna try and sprint us through.
So we don't graph the base.
We are not graphing the exponential. We are graphing our logarithmic parent. We need this to make this, but this is what we're going for. This is the guy we want to have. We just use this as a tool. So, 3 tables, 2 graphs, and a partridge in a pear tree. And an asymptote, actually. Okay. So, we've got our homework 8-1 is due on Friday. You guys can get started on those graphs, especially we can get those parent functions graphed on there. And if you want, you can save those transformations to do tomorrow. So we're going to look at stuff, see what we can do.